Good morning, Spartan fans. I'm going to discuss properties of rational functions in this video. So how much of it you watch is up to you. You are responsible, however, for understanding how to find the domain and range of a rational function. So 1 over x is one of the parent functions, and it's on like that gold sheet that we talked about probably 2 weeks ago already. And it is the only function that does not have a domain of all real numbers. So in this problem, x cannot be 0. Division by 0 is always undefined. So if there's a denominator, you gotta watch out. The parent points are 1, 1, and it's a branch that looks like such. And it has a horizontal asymptote on the y-axis as well as on the x-axis. So there's a horizontal asymptote on the y-axis because x can never be 0. So that causes what we call an asymptote, and it is a line that the graph approaches but never touches. It's a line the graph approaches but never touches. This graph also goes through the point -1, -1, and these curves are also often referred to as branches. Okay, so the domain of this function is all real numbers, x not equal to 0, and the range is also all real numbers, but y not equal to 0. Okay, I'm going to go back and I'm going to review some shifts. So for the parent functions, we have a x minus h quantity squared plus k. Or maybe it's a the square root of x minus h plus k. Or maybe it's a times x minus h cubed plus k. And these should all have a y equals. Maybe it's a times the cube root of x minus h plus k. Well, guess what? For the rational function, it's a over x minus h plus k. H is the horizontal shift. So essentially what's happening here is instead of shifting the vertex, what we are doing is shifting the asymptotes. Okay, so I'm going to go through a couple examples. And again, how much of this you want to watch is obviously your choice. So let's look at something such as y equals 1 over x plus 3 minus 2. Okay, so this is going to be a shift left 3 down 2. And so what happens is we are shifting the horizontal asymptote, which is normally at x equals 0, and we're shifting the vertical asymptote, which is normally at y equals 0. So I'm going to draw a really small little graph here. Hopefully I can fit it in. Left 3 down 2. I may need to bag this graph and do a different one. Hopefully I'm going to get lucky and it's going to fit. So down 2, I'm going to have an asymptote at y equals -2. And left 3, I'm going to have a vertical asymptote at x equals -3. And so my new origin, let me just draw this in a little, let me highlight it. So my new origin is this point right here. This is my new origin. So from my new origin, I'm going to plot my parent points, 1, 1. Oh, I did. That's not very good. Let's try that again. 1, 1, and negative 1, negative 1. And there are my branches. So my domain is all real numbers. X can't be negative 3. If X is negative 3, negative 3 plus 3 is 0, and that is never allowed. My range is all real numbers, y not equal to negative 2. All right, what happens if there's an a value? Okay, so here we go. Let's do something like y equals negative 3 over x minus 1 plus 4. This is kind of an obnoxious bar there. Okay, so x cannot be 1. If x is 1, 0 in the denominator, no can do. So this is where my vertical asymptote is going to be. Vertical asymptote, VA. Up 4. So that's where my horizontal asymptote is going to be. Okay, so let's just start here. Let's just graph these asymptotes, and then we're going to take care of the fact that a is negative 3. We'll do that in a minute. And let me draw a little bit of a nicer graph here. Whether the graph is absolute value or a quadratic or a root, how you determine the right-left shift is always the same. The difference is going to be the actual parent function. So right 1, that is going to be a vertical asymptote. X cannot be 1, vertical asymptote. Up 4, that's going to be y is 4. Okay, in this problem, a is negative 3. My parent points are 1, 1, and negative 1, negative 1. So the parent points, that comes from y equals 1 over x. There are many, 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 many points that are on this graph. 1, 1's the easiest. And negative 1, negative 1. You can use whatever points you want. I'm sticking with the easy ones. A is negative 3. So I'm going to take my y values. I'm going to multiply by negative 3. So 1, 1 becomes 1, negative 3. Negative 1, negative 1 becomes negative 1, positive 3. So from my new origin point, so my new origin is right here. I highlighted it. I'm going to plot the point 1, negative 3. That's here. And I'm going to draw my graph. And the point negative 1, positive 3. And there's your graph. The domain, all real numbers, x not equal to 1. And the range, all real numbers, y not equal to 4. Okay. Let's take a look at not graphing, but just talking about domain in general. Domain always comes from x, your input. And when you're talking about a rational function, so a rational function, a function with a variable in the denominator, a rational function has a variable in the denominator. And if there's a variable in the denominator, that's an issue. That has 1 over x plus 2 has a variable in the denominator. That's a problem. The domain, without graphing it, is going to be all real numbers. X can't be negative 2. Negative 2 plus 2 is 0. Yuck. Y equals 3x over x minus 6. I could care less about the 3x. The 3x has no effect on the domain. What I care about is the denominator. If x is 6, that's a problem. So the domain is going to be all real numbers. X can't be 6. So what if it's something like y equals 4x over x squared minus 9, let's say. We're not going to graph this. The question is, what's the domain? 0 in the denominator is never allowed. 0 in the denominator, that's it. The world's going to blow up. 0 in the numerator, fine. Who cares? All I care about is the denominator. You can totally ignore the 4x when you're trying to figure out the domain. So you've been doing this. X squared minus 9, where does that equal 0? That's going to determine my domain. Add 9 to both sides. Square root. X is plus or minus 3. So my domain is all real numbers, x not equal to 3 or negative 3. Okay, I'm going to do one more. How about something like some function, whatever, x plus 17 over, don't care, the x plus 17 has 0 effect on the domain. What I care about is the denominator. How about something like x squared plus 4x minus 5? Okay, so what I care about is x squared plus 4x minus 5. What values of x is going to make that 0? So I'm going to set it equal to 0. And now this is a factoring problem. It factors as x plus 5, x minus 1. So we've been doing this now for a little while. So x is negative 5 and positive 1. If x is negative 5, when you plug this back in, if x is negative 5, you're going to get 0. If x is 1, you're going to get 0. Cannot happen. The domain, all real numbers, x can't be negative 5 and 1. We'll worry about the range later, but what I care about right now is the domain. You know what? Sometimes, even though there's a variable in the denominator, sometimes the domain could still be all real numbers. So an example of that would be something like the f of x is equal to 2x squared minus 7. Who cares? That could be anything, doesn't affect the domain. Over something like, how about x squared plus 4x minus, now how about plus 7? So again, what I care about is where does the denominator equal 0? Okay, well, when you go to solve that, you're going to say, okay, x squared plus 4x plus 7 equals 0. And to my knowledge, it cannot be factored. So unfortunately, you're going to have to use the quadratic formula. And so that's going to be b squared minus 4 AC all over 2a. Well, when you simplify this, you're going to get negative 4 plus or minus the square root of negative something or other, 16 minus 28, negative 12 over 2. This is imaginary. Okay, so what this means is every value that you plug in for x is not going to be 0. Every value that you plug in for x will not yield, how about we say will not result in 0. Every value that you plug in for x will not result in 0 in the denominator. X can be anything I want. Okay, so therefore, the domain is going to be all real numbers. So, like in this problem that I did up here in orange, if you plugged in negative 5, the denominator was going to be 0. Nope, that's not allowed. If you plugged in 1, the denominator was going to be 0. Not allowed. In this problem, the previous one up here, if x was 3, 0 in the denominator, not allowed. If x was negative 3, 0 in the denominator, not allowed. In this last problem, it's imaginary. So that means that there's no number that you can plug in for x that's going to give me 0 in the denominator. All the x values are okay. Hence, the domain is all real numbers. Okay. I'm going to just show you a couple examples from the book. Clearly, if you want to stop the video at any point in time, feel free. You are asked in some of the homework problems to analyze a graph, which I think you can probably do by looking at the graph, but I'll do one example just to help you out. I think that you know how to look at a graph and understand how to find the x and the y intercepts. So I'm just completely, totally randomly making up this graph. Let's say that there is an asymptote at y equals 2. Sorry, that's x equals 2, not y equals 2. And there's an asymptote at y equals 1. And the graph goes through the point. I'm literally just making this up off the top of my head. The graph goes through the point 0, 3, and how about 5, 0? It would be nice if it actually went through 5, 0, huh? Okay, and so if I asked you to analyze this graph, if I asked you to find the domain, okay, so looking at the vertical asymptote, the vertical asymptote is at x equals 2. Therefore, my domain is all real numbers, x not equal to 2. The range, that's going to come from my horizontal asymptote. So y can be any value that I want, except for 1. The x-intercept is given to you. The x-intercept is at 5, 0. Make sure your proper notation. So there's a couple problems in the book where you're asked to analyze the graph. Y-intercept is at 0, 3. The horizontal asymptote comes from your range. Horizontal asymptote is at y equals 1. Vertical asymptote is at x equals 2. So there's a couple problems where you're asked to analyze the graph. Okay, when I'm back in class, I will go over all of the homeworks. There'll be a couple that we need to review. There is a Desmos. Make sure you're doing the Desmos. It is due before you leave class.